Alright guys, so in this video we want to correct a few exercises. Having looked at, having reached this far and, looking at everything we've done, I think it's best that we correct a few exercises. Now let's look at this first exercise that we are supposed to correct together. So let's look at the question. Pour chacun des sous-espaces vectoriels f et g de R3 suivants, déterminer s'ils sont en somme directe. So we have number one, we want to determine if f and g are ensemble direct. So remember that to be able to show that two vectors are ensemble direct, the necessary and sufficient condition is to show that their intersection contains the zero vector, contains only the zero vector. So if the intersection contains only the zero vector, then we can be sure that that the two vectors are going to be ensemble direct. So for the first exercise, what we're going to do is that we're going to show that the intersection of the two, les deux espaces vectoriels f and g, that their intersection contains only the zero vector. So we'll do the same thing for exercise number 2. Now let's look at what we have here. Now the first thing that we have to observe here is that f is a sous-espace vectoriel of R3, just like the question is saying. And then also g is also a sous-espace vectoriel, of R3. Okay, if you want, you can quickly verify that it's actually a sous-espace vectoriel. So we have to find out whether the zero vector of R3 is in the espace vectoriel F. So if you plug in 0 for x, 0 for y, and 0 for z, you will see that this is going to satisfy this equation that we have here. So we're going to have 0 is equal to 0. So F contains the zero element of the parent espace, which is R3. So we have that F is non-empty. So you check, you find that it's the same thing for G. But for G, we have two equations to satisfy. So if you plug in your 0, 0, 0 in these two equations, you get that the sous-espace G is going to be non-empty, right? And then you can also prove stability by addition, which I believe is very easy, and stability by a scalar multiplication. That is for F and for G. So now, what we're going to do to be able to solve this exercise, remember that we're supposed to show that the intersection contains only the zero vector. So what we're going to do is that we're going to take a vector from the intersection of F and G. Now, a vector in F has 3 components, a vector in G has 3 components. So what we're going to do is that we're going to choose some vector that has components x, y, and z. We're going to take it from the intersection, and then we're going to show that that vector is actually the zero vector. So let's look at how that is going to work. So let me just maybe choose this color like so. Now let's choose some vector in F and G. So we're going to say soit x, soit le vector x, soit le vector u, which is equal to this vector. So we can call this vector u if you want, so that you maybe, donc soit u, a vector that has components x, y, and z, that is in the intersection of F and G. So what does it mean for F to be, what does it mean for the vector u to be in F? So if u is in the intersection of F and G, this means that the vector u is in both F and G. So what does it mean for u to be in F? So what does it mean for u to be in F? So for u is in F, this means that the vector u satisfies this condition that we have here for F, this condition. So it means we're going to have x plus 2y plus z is equal to 0, right? So what does it mean for the vector u to be in G? So the vector u is in G if it satisfies the condition that comes with G. So what condition comes with G is that a vector is in G if it satisfies these two equations that we have here, right? So it means we're going to say if u is going to be in G if it satisfies the two equations. So we're going to say 2x plus y plus 3z is equal to 0. And then here we have x minus 2y minus z is equal to 0, like so. So if u is in the intersection, it means it has to satisfy all these 3 equations. It has to satisfy all these 3 equations. Now this is going to mean that if u is in F intersection G, it means that u has to satisfy the 3 equations that we have here. So x plus 2y and then plus z is equal to 0, like so. And then 2x plus y plus 3z is equal to 0. And then you have x minus 2y minus z is equal to 0. Right. So this looks okay and this looks good. Now, remember, we're supposed to show that u is the zero vector, right? Because we have to show that f and g are ensemble direct. To be able to show that, we have to show that the only vector that is in f intersection g is the zero vector. So to be able to at least arrive at a solution, we must solve these equations. Okay, we must solve these three equations. So how do we solve a system of equations? So you can employ any method you want to employ here. You can use your matrix method. You can use any method you want here to be able to solve this system of equations. So what I'm going to do is I'm going to use this method here, and of course you're free to choose any method you want, any method that is going to lead you to the correct solution. But the method I'm going to use is this method. So I'll continue solving. So I'm going to leave the first line. So I'm going to call this one la ligne 1. This one is going to be la ligne 2. This is going to be la ligne 3. So I'm going to keep la ligne 3 constant. So I'm going to say x plus 2y plus z is equal to 0. I'm going to keep it constant. Then I want to eliminate x. Okay, the first variable I want to eliminate in the next two equations is x. Okay, so how do I eliminate x here? How do I eliminate x here? So la ligne 1, this is still la ligne 1. So how do I eliminate x in this second equation? Well, I'll eliminate x if L2 receives the value. If L2 receives the value L2 minus 2L1. Now you can see that to be able to eliminate this x that we have here, we must multiply 2 we must multiply 2 by the first equation, and then when we subtract, we'll get rid of x. Okay, so when we subtract here, verify that you're going to get minus 3y plus z is equal to 0, like so, because it will be 2x minus 2x is 0. Then it will be 4y. It would be right. So here, what are we going to have? We'll have 3y, like so. So 2x minus we have 2x minus 2x is 0, so that is why it disappears here. Then we've multiplied the first line. We've multiplied the first line by 2. Okay, we've multiplied the first line by 2. Then we say so here you must make sure that you have this format here, L2 and then L2 starts here. So you don't do it the other way. So L2 starts like so. That's when it makes sense. Okay, so L2. So you see that we'll do the same for L3. We'll follow the same rule for L3. So now this is going to be 4. This is 1. So here it's it's y minus 4y, which gives us minus 3z, and then plus here it's 3z minus 2z, which gives us z is equal to 0. So we'll do the same thing. So, but we'll keep the first line constant. Then in the third line, just like we did for the second line, we want to get rid of x. So here we have to do la ligne 3 is going to receive la ligne 3 minus la ligne 1. Here we don't have to multiply anything because we have x and then we have x here. Then if we subtract here, verify that we get minus 4y minus 2z is equal to 0. So let's check. So here we don't have to multiply anything. So we are saying la ligne 3, so ligne 3, like so. So la ligne 3, c'est x moins x, which gives us 0. And then it's minus 2y, which gives us minus 4y. And then minus z minus plus z, which gives us minus 2z, which is equal to 0, like so. So you can see that it's becoming slant. So this is known as, we are sort of like reducing this system, right? We are reducing this system. Okay. So now, since we've gotten rid of x, the next thing that we want to do is we kept the first line constant here. Here we kept the first line constant. So here we're going to keep the first line and the second line constant. So in the next iteration, we'll keep the first line and the second line constant. And then we're going to change the third line using the second line. So here we changed the second line and the third line using the first line. Here we'll keep the first line constant and the second line constant, but then we'll change the third one using the second line. So here we're going to get, so here I'll keep the first line constant. So you keep x plus 2y plus z is equal to 0, like so. Then we keep the second one constant. So we'll have minus 3y and then plus z then is equal to plus z is equal to 0, like so. Now here, I think it's actually simpler to sort of like get rid of z than get rid of y. So what I want to do is to change the positions of x and y, because here I have to multiply by 4. Here I have to multiply by 3 and by 4 if I want to eliminate the y. So that is actually more complicated. So what I want to do is, because the sum is going to be, you know, associative and commutative, all that, we can make use of those properties. And then I'll say x plus z and then plus 2y is equal to 0. And then here I'll say z minus 3y is equal to 0. Then here I'll say minus 2z. So you can see that it's actually easy that you know, that way. So minus 2z minus 4y is equal to 0. So it's actually easy to get rid. It's easier to get rid of z than to get rid of y. So I'll continue with my calculation. So we leave la ligne 1, la ligne 2 constant. Then we're going to change the last one using the second one. So here what we're going to do this operation. We're going to do this operation. La ligne 3 reçoit. The line 3 becomes la ligne 3. So you can see that I follow the rule. La ligne 3 reçoit la ligne 3 plus 2 fois L2. So here if I multiply 2 by the second line, you can see that we're going to have the coefficients are going to be equal. The coefficients for z in line 2 and line 3 are going to be equal in magnitude. So if I add them, the first one is positive, this one is going to be positive, but then this one is going to be negative. And so I'll get the following system. I'll get the following system. Okay, I'll get the following system. Okay, so here this is what we have. But then this I have to write it on the next line. I have to write it on the next line when I actually make the changes, when I actually make the update. When I actually make the update, that's when I want to write it. Okay, so and then that is going to make, you know, more sense. It's going to make more sense. Okay, it's going to make more sense. I actually swapped the lines. I mean the value. So x plus z plus 2y is equal to 0, like so, and then z minus 3y is equal to 0. And then here we're going to get minus 10y if we perform that update that I said. La ligne 3 reçoit la ligne 3 reçoit. So here we can say la ligne 3 reçoit la ligne 3 plus 2 fois L2, like so. Oh, now you can see that it's actually easy for us to find the value of y, right? Because all we have to do here is to divide by minus 10 throughout. So this is going to mean that our y is equal to 0. So if you found the value of y, you can see the beauty of this method. Since we found the value of y, we just have to at least go up one step, like so. So we plug in the value of y that we found. So if I plug in the value of y that I found here, I'll get z is equal to 0. Again, I keep going a step up, like so. I'll plug in the value for y and then the value for z. Then this is going to mean that x is equal to 0. Now here, our choice of this vector x, y, and z is arbitrary. You can see that it's arbitrary because here this is the general expression of a vector that is going to be in the intersection. So because our choice of the vector u is arbitrary, we can confirm that actually the intersection is reduced to the 0 vector. So here we can confirm that x, y, z, the vector that we've chosen from the intersection of f and g is actually going to be this 0, 0 vector. Then this is going to mean that the two vectors, spaces f and g, sont ensemble direct. So ensemble direct, like so. So this is what we have. Okay. So that is for the first exercise, for the first problem. Now let's look at the second problem. Let's look at the second problem and what we can do. So for the second problem, still we're going to repeat the same steps. Okay, we're going to repeat the same steps. So let's try, let's keep going, let's keep going. Bien. So though we've not, talked about solving systems of equations, in great detail, but again, we can sort of like, pick up a few techniques and all that. And you see, especially for the second one, we'll have something that I'll tell you that we'll discuss in great detail a little later. So same, we'll choose a vector in the intersection. So here you can check, first of all, the first thing that you have to do is to check, is f a sous-espace vectoriel of R3? Is G a sous-espace vectoriel of R3? I believe that is important because, I believe that is important, and it's something that you must check before you even solve the problem. Okay, so right, so let's look at this one. You can see that the sous-espace f is, the espace f is non-empty. Same, G is non-empty because if you plug in 0, 0, 0, 0, you see that the condition for f is going to be satisfied and the condition for g is going to be satisfied, then the others are easy to check. You can sort of like look at the, look at what we have, and then you'll be able to understand. So again, we choose a vector in the intersection. So soit u, a vector that is equal, that has the following components. Okay, soit u, a vector that has the components x, y, and z. So we're taking it from the intersection, like so. We're taking it from the intersection. What does it mean for this vector to be in the intersection? It means that this vector is both in, it's in f and then it's also in g. So it means it satisfies the condition for f and the two conditions that we have for g. So if it is in the intersection, then this is going to be equivalent to saying that this system of equations is supposed to hold true for this particular vector. This system of equations, sorry. So x plus y 2z is equal to 0, and then 2x plus y plus 3z is equal to 0, and then x minus 2y minus z is equal to 0, like so. Okay, x minus 2y minus z is equal to 0. So let me just check if I've written the correct thing. 2x plus y plus 3z, 2x plus y plus 3z, and then x plus y plus 2z. So just like we solved the previous one, we also do the same thing for this one. So the first thing that I want to do is to sort of like push this, put it here. So let me just write it here so that we can. So look, we're going to keep the first line constant. So we're going to say x plus y and then plus 2z is equal to 0. Then we get rid of x. Okay, we get rid of x. You can change the positions of the variables if you want, or if you want to sort of like have simpler values to eliminate. So here x, the coefficient is 1, so it's actually good that I eliminate it. So I need to now modify the second line. So if how do I modify the second line such that I get rid of x? Well, the first thing I have to do is to perform this operation. I know I'm supposed to write la ligne 2. So this is la ligne 1, la ligne 2, la ligne 3. The first operation I'm supposed to perform here is la ligne 2. What is la ligne 2 going to receive? So L2, I'm supposed to write L2 here. L2, L2, like so. L2, L2. I'm supposed to write this. Okay. Then what must I do to the first one? To first of all make the coefficients equal, and then what operation must I take between the two constants? So you see that here the operation is going to be a minus, and then I have to multiply the first line by 2. So 2L1, like so. This is going to give us, if you apply this, you get minus y minus z. Let's check if this is actually going to be the case. So here we have 2x minus 2x, which gives us 0. Okay, and then we have y minus 2y, which gives us minus y, and then we have 3z. We have 3z minus 4z, because this will be multiplied by 4 by 2, so it becomes 4, so it's going to be minus z. Okay, then what are we going to do to the third line? So we're going to say L3 reçoit. Again, you write L3. Now we have to think about the operation and how to make the coefficients equal. Well, here we don't have to make the coefficients equal because we already have 1, 1. So this is actually a simple operation. So c'est L1, c'est L3 moins L1. So if you perform this operation, verify that you're going to get this particular line. So minus 3y minus 3z is equal to 0, right? So up to this point, I hope everything is okay. Now let's look at these two lines here. There's something in common. These two lines have something in common. So what we're going to see here is, what we observe actually here is that, look, I'll write the first one the way it is. X plus y plus 2z is equal to 0. So let's look at this second line here. If I factor minus 1 out, I'm going to have y plus z is actually going to be equal to 0. For the last one, if I factor minus 3 out, it's going to be y plus z is equal to 0. So you can see that we have the same line. Okay, we have the same line. So here we can divide minus 1. Here we can divide minus 3. Such that what we have in the end is, so you have x plus y plus 2z is equal to 0. Then here you're going to have y plus z is equal to 0. And then here you have y plus z is equal to 0. So we can actually see here that it's the same line. So we have the same line. So if we have the same line, what we can do is that we're going to get rid of one of the lines. Okay, we get rid of one of the lines because this y plus z is equal to 0, y plus z is equal to 0. We don't have to write it twice. So we get rid of one of the lines. So we get rid of this line, for example. So you can also get rid of the second one if you want, so that you have the first one and the second one. So that is going to be, that is going to give you the same thing. So finally, what we have here is going to be, so x plus y plus 2z is equal to 0. So these two lines are linear. So we get rid of one. So here we're going to have y plus z is going to be equal to 0. So here, what do we get? Here, this one possible, so here we're going to have that y is equal to minus z. Now, since we found the value of y, we have to go up like so and replace the value for y that we found, so that we can find the value for the other, we can find the value for the other variables. Okay. So here, if I plug in the value for y that I found, I'm going to have x and then minus z plus 2z. Minus z plus 2z is x plus z. Okay, we're going to have x plus z in the end. Okay, so here I've replaced the value for z that I found. So here I'll put minus z. Let me just maybe write it like so. Then minus z plus 2z. Minus z plus 2z gives us what value? It's actually 2z minus z, which gives us z. So it means if you make x a subject of the formula, you'll be able to say or conclude that actually here x is going to be equal to minus z, like so. Okay, you see that x is going to be equal to minus z. Here, if you substitute minus z, you add the two equations, you add the two terms, the two common terms. So it will be 2z, it will be 2z minus z, which gives us z. So you have x plus z. Then you make x a subject to the formula, you get x is equal to what? You get x is equal to minus z. You get x is equal to minus z, like so. Yeah, so this is okay. Then here you can see that nothing has happened to z, right? It's like we don't have a value for z. So, but what we can do here is, z is actually going to be equal to z, because we from the equation we cannot sort of like conclude what value z is going to have. So this is going to imply that this vector u that has components x, y, and z is going to be equal to this vector. So the x here is going to be minus z. Then the y here is going to be minus z. Okay, the y is going to be minus z. Then the z is going to remain z, like so. Okay, so this is what we have, like so. So what we're going to do next is to factor out. So we have z, like so. Okay, so z is common here. Z is common. Okay, z is common. So what we can do here is that we can factor out the z. Okay, so if you factor out the z, you see that z is going to be, if you factor out the z, you're going to have minus 1, and then you're going to have 1, like so. If you want, you can factor out the minus z, such that you have 1, 1, minus 1. Okay, so you can see that this vector that I've written here, let me just call it w, is one solution. There are many solutions. Okay, it's a possible solution. This vector w is a possible solution of this system that we have here. Let's check. So let's check if this is a solution. So minus 1, 1. Okay, so let's check if this is a possible solution. All you have to do is to get these values and plug them here. Okay, and plug them in here. So x is minus 1, y is minus 1, z is 1. So here you have a minus 1. Let's check together. Here you have a minus 1. Here you have a minus 1. Here you have a 1. So this minus 1 will give us minus 2, plus the 2 will give us 0. Okay, so here you have, for y it's a minus 1, but then with this minus you have a 1, but then z is positive, is a positive 1, so you have 1 minus 1, which is 0. Okay, so you check this one, you get this, you get this, oh, well, actually supposed to check this here. Okay, actually supposed to, but it's the same thing. We actually are supposed to check here. So you get this minus 1, you plug it here, you get minus 2. Same thing here, you get a minus what? You get a minus 1. So you get minus 3 plus 3, which is equal to 0. So you can see that even the last one is also going to work. So you plug in your minus 1, here you have minus 1. You plug in your minus 1, here you get what? What are you going to, here you have a minus 1, so you have a minus 1. Here you have a plus 2, like so. So minus 1 plus 2 will give us 1. And then if you plug in your 1 here, you have 1 minus 1, which is going to be equal to 0. So this is a solution. So it means that because we've been able to factor by, we've been able to represent u as, if u is collinear, so here we've been able to represent u en fonction de a certain vector that we are calling w here. So we can see that here, this vector minus 1, 1 is actually in the intersection of f intersection g. So the two vector spaces f and g for the second question cannot be on some direct, because if they are supposed to be on some direct, the only vector that is supposed to be in the intersection is the 0 vector. So this means that the intersection has to be reduced to the 0 vector. Here the intersection is not reduced to the 0 vector, okay, because we have this solution. So the intersection is not reduced to the 0 vector. Alors f et g ne sont pas en somme directe. Ne sont pas en somme directe. So hopefully you're able to, understand how we can sort of like go about solving this particular exercise. So it's very simple. So be very careful when you're solving these, systems of equations, and rewatch the video so you can see what I did for the second one, and how what I did for the second one compares with what I did for the first one. So otherwise we're going to move to another interesting exercise.